Jason Skinner next, which we've got the talk Industrializing MRI from preclinical to millions of scans at record-breaking throughput. Jason Skinner is a staff MR scientist at Orbem and imaging tech lead for the in vivo sexing application, which I'm very interested to hear about. He has a background in preclinical and hyperpolarized MR, spending much of his time in academia in proof of concept experiments. At Orbem, his focus is currently on scaling while pushing the limits of acceleration with AI-powered imaging. So some really great sort of words there to look forward to. I'm looking forward to hearing from you, Jason.
Thank you. Thank you very much, Tim. Hello, good morning, good evening. My name is Jason Skinner, staff MRI scientist, as Tom just said, at Orbem. It's a startup with many of the characteristics actually that Kevin was sharing before. So there's a lot of common messages that I will be talking about. For example, you can find many PhDs at Orbem that are all quite excited about developing a disruptive technology, especially one that's based on MRI. And actually, that's what I wanted to start with. I wanted to show you what Orbem does and this disruptive technology that we've been developing. Do you see the video? I see a blank slide.
We can see the video. We can't hear it.
Okay, nice, thank you. So what does Orbem do? We're industrializing MRI, and what you see on the screen here in the video is our first product, which is the Genus Focus, with which we scan eggs. We scan eggs non-invasively, of course, it's an MRI. And the reason we do that is to classify the embryos within the egg as either male or female. And you can see here that it's fully automated solution. It's fast, there's a continuous flow. It integrates seamlessly into the hatchery environment because it's supported by a lot of automation equipment. So you saw the pick and place robots, for example, taking eggs from the tray and loading them onto this single line where they're then passed through the MRI scanner. And you saw a couple of them just there. So we now follow the journey of a single egg, and as it's going through the scanner, undergoes a scan with a duration of around 1 second. Before it reaches the other side to the rest of the automation equipment, it's already classified and then sorted. So this automation equipment is then, here you see, separating the female embryos, separating them from the clear and the male eggs, which are then discarded here. And the impact of this is really huge. There's a really big animal welfare impact here because by doing this, we avert the need to cull male chicks after they're hatched, and instead we can classify and sort them at this earlier stage in development and avoid any needless suffering or culling of these male chicks. The solution, the Genus Focus, it can be operated by a single operator, and you can see that it's modular and expandable. And at the end of the process, the eggs are then returned to the incubators. The female eggs are returned to the incubators to continue the incubation and development process. So that is the Genus Focus and what Orbem has been working on for the last few years. And so I'm going to share a little bit about how my journey in academia and the skills that I developed, and whether they were transferable and in what way they were transferable to industry. But first, before I go, I'm going to jump straight to my PhD. But first, I think 30 seconds of science is necessary because I'm going to be talking about this concept a lot. So what is hyperpolarization? In the top left, you see the situation that plays out in conventional MRI. So the spins are aligned according to Boltzmann thermodynamics, the Boltzmann statistics. And what it means is in your sample, when you put it in the scanner, all of these spins align, but many of them oppose each other. So in this diagram, there's one spin that contributes to the signal. And this is why we have a low signal generally when we're doing MRI. And then this concept of hyperpolarization, you can see this acronym COP at the top, it's spin exchange optical pumping. Using this or other techniques, you can manipulate these spin states and therefore also the magnetization. So you see this big bold black arrow now in panel B. We've got this much stronger signal and it gives you 100,000-fold, for example, enhancement in signal. And you see that in the bottom right, this hyperpolarized xenon signal. And you're going to hyperpolarize several different things. So I'm going to talk about xenon. I'm also going to talk about carbon-13 biomolecules such as pyruvate, with which you can probe metabolism. And you can also do other things like pH mapping if you can find a molecule, a carbon-based molecule that has chemical shift sensitivity to pH, for example. And the key thing about this is that while you can make this enhancement, it's very delicate and it only lasts a short amount of time. So this has to be considered. Okay, so the story of my PhD, I'm going to start it kind of at the end with this image. And it's an unremarkable image, I think, in quite a number of ways. However, it's also a milestone image and significant to me because it represents basically the culmination of my PhD and the thing that I built. And more importantly, for this talk and the focus of our discussion, I learned a lot of skills and overcame a lot of challenges to create this image. And this image is actually hyperpolarized xenon, and it's in a Tedlar bag, which is a kind of bag that you use to then administer that to volunteers or patients. And it was acquired in the last month of my PhD, a 4-year PhD at the University of Nottingham. And yeah, I'll talk a little bit now about the skills and challenges on the way to creating this image. So starting in the top left, if you want to do spin exchange optical pumping to create hyperpolarized xenon, you need another ingredient, which is rubidium. And that is something that's highly reactive with oxygen. So in the top left, you can see a glove box in an inner atmosphere. And there I was learning skills, right? I was learning the experimental procedures to do these kinds of experiments. And then, of course, I was spending a lot of time collecting data, planning experiments. And in the next image with this green light, this is actually a laser. And something else within that cell that you place there is nitrogen. And this acts as a buffer gas, but what it enables us to do is to also characterize the cell in different ways. So to characterize the temperature using Raman spectroscopy. And to get those insights, it was then necessary for me to write some code, some algorithms to analyze those spectra. So there I was developing code for this purpose. And then next in the bottom left, you see the beginnings of a xenon hyperpolarizer. So what you see here are 3 subsystems of the polarizer. And in order to do optical pumping, the first part, you need a laser with circularly polarized light. So that's what you see in the left of the image. You need an oven, which is 3D printed inside those coils. You need a magnetic field to do Zeeman splitting to enable the optical pumping. And you can see those 3 black circles there are electromagnetic coils that were installed and then calibrated. And there's also an NMR spectrometer, actually, that's just off screen. And so what did I learn at this point? It's all about hardware characterization, about calibration, about hardware integration, about debugging, bringing these things together, running experiments and iterating and so on. If we look at the top right of the slide, you can see that I also ran some numerical simulations of spin exchange optical pumping under relevant conditions to get the most out of the polarizer. So this means I was doing another kind of coding, right? I was exploring the theory of spin exchange optical pumping while leveraging numerical simulations to arrive at optimizations. And then finally, it was all brought together within the 4 years. And you see in the bottom right there, the almost fully assembled polarizer that made it a short journey from the Department of Physics at the University of Nottingham across to the Queen's Medical Centre, where it's used now for functional lung imaging. And beside these skills, there's another theme as well that I wanted to emphasize, and it's one of innovation. So what we're doing here is hyperpolarizing xenon, but with a vision of doing this with a press of a button. So like a coffee machine. And this is something that wasn't possible before with previous designs of xenon polarizers for various technical reasons. So there was this innovative element to it as well. Okay, so after my PhD, I continued with this theme of hyperpolarization, and I've now switched from xenon to carbon in a biomolecule. And you can see the enhancement on the left. And now I've learned some more skills. I'm starting to branch into MRI and develop skills in sequence development and protocol optimization. but there's also this innovative element that goes along with it. And here it was about, well, I've already got one big machine, this MRI scanner. Do I really need this second big machine, this polarizer? And actually, given that the T1 is so short and that the signal is so precious and delicate, what if we just got rid of the polarizer and we polarize inside the MRI scanner directly and then inject the subject within the scanner? So that reduces the time, it reduces the signal loss, and it reduces the footprint of the hardware. So this was the concept here and the step forward in terms of innovation within this space. And that was, I should say, sorry, that was done at the Universitätsklinik Freiburg, so the medical physics department there. And then on to my second postdoc. This is 2 of 2 at the Department of Nuclear Medicine at the Klinikum Isar in Munich. I continued down this path of MRI and innovation, of course. And the innovative thinking that combined with the hard skills here was, how do we take this very precious hyperpolarized signal that is actually really rich in content in terms of the information and the insights that can be derived? Because now we have 2 signals, we have 2 resonances, different chemical shifts. One is pyruvate, and that's the thing we hyperpolarize and inject. And this is metabolized to lactate. And this is a process that happens over time, and it happens in space. And as I said, 2 chemical shifts. So we have 3-dimensional and through time and spectrally as well. So my approach was to develop a 3D BSSFP sequence, and each image was taking around 1 second to acquire. And then this would alternate between the 2 different chemical shifts, and also alternate in flip angle to try and preserve the signal on the pyruvate and maximize the signal of the lactate. There are also many soft skills that I developed to this point as well, because these experiments are actually very complex and they have to be executed also very quickly and precisely. So they're done in collaboration also with veterinarians, for example, and chemists who are involved in the polarization. So a skill I developed here was simplifying complex concepts and communicating this kind of information that was known from the MR sequence development side, for example. Okay, and 2 more projects from this postdoc. There's a continuation of this theme of innovation and extension of what we could do with the sequence. So on the left, you can see that we were able to work with a molecule that was already developed within the lab there. So in the lab of Professor Fran Schilling, a molecule called ZONPD, and it's a pH-sensitive molecule, and also had a remarkably long T1. So we were thinking, how can we rethink clinical approaches? And is it possible to combine a couple of measurements into one and leverage the properties of this molecule and this sequence? And we were able to combine it into a 3D perfusion imaging sequence followed directly by a 2D pH imaging sequence. In the center here, you see a pH map of the kidneys. And this was a great proof of concept organ to target because of the strong pH gradients that you see within the kidney. And then another learning or innovation, like Han, I'm trained as a physicist, and actually I had no training in deep learning or AI as part of my undergrad or master's or even throughout my PhD. So I'm starting to look around and the writings on the wall that actually there's a lot to do with AI and deep learning. And so I asked the question, can we leverage deep learning to get more out of these pH maps? And together with the team, we were able to get more out of these pH maps in situations where the peaks were starting to overlap or in low SNR situations. Okay, so that is my journey, academic journey in a nutshell. And I think you have an idea of my profile and interests and the skills I've developed along the way. So then in 2022, after these 2 postdocs, I joined Orbam. And in that time, Orbam was 11 people, and they had a clear mission and purpose and already a really strong, positive, established culture. They had 1 proof of concept scanner and an idea, a clear idea of what they wanted to do, but obviously a lot of work to do to realize that. and scan times of over 5 minutes per egg. And when I say 5 minutes per egg, that means to reach a resolution where we can get a classification of a good accuracy. So to accurately classify based on the image. So fast forward to 2024, I think this photo was from the summer of this year. We've secured over 30 million in funding. There's over 140 employees now, so it's really grown. 40 different nationalities, so it's really diverse, a lot of different backgrounds. To date, we have scanned and classified over 77 million eggs. So this really is an industrialization of MRI and MRI at scale. And to do that, that's been supported by 20 scanners that are installed and operational at various customers. And we've also reached a scan time of 1 second per egg now. So this is a big acceleration from when I was joining Album. What skills were transferable? Before I talk about those that transferred, I just wanted to talk about some new skills that became quite prominent during the time, these 3 years that I've been at Album. And I would say planning and prioritization. There's always a lot of this to do, as we are planning every 3 weeks for our sprints, and then there's also quarter planning, and we get together as a company and make plans for the next quarter. There's a lot of teamwork, as Kevin mentioned as well. It's very different in nature. That was a great description given by Kevin. There's a lot of negotiation and persuasion that goes into this as well, as you can imagine, when you have these different priorities with the different teams and you're trying to align on how do we best move forward together. And there's also, in contrast to academia, a big focus on robustness and quality and stability. That you don't see because the scales are different between industry and academia. And now, if I tell you the team that I work within is the performance for Innovo team. So that means we have ownership of optimizing the throughput and performance of our scanners. You can imagine the kind of work that we're doing, right? And it's very much an intricate link of imaging protocols paired with models. We do this AI-powered imaging. And if you think about the nature of the work there, about data collection, about iteration, about processing, analyzing, communicating, I think you can start to imagine how many of the skills I've already talked about through this academic journey are applicable in this case. And the answer is all of them, right? Everything that I've done on that academic journey, I'm using all of these skills in my day-to-day work at Auburn, including this innovative mindset of, how do we change this thing, or how do we rethink MRI or calibrations or these various things to try and reach this goal of scaling with as little variation as possible and going as fast as possible. The only difference I would say is that is the magnitude and frequency, like the way that these skills are used and the intensity. For example, communication is by far the biggest skill I'm using on a day-to-day basis. And I'm constantly thinking about how do I communicate this point, or what is relevant to communicate, or how do I adjust my communication? Because all of this is key for decision-making, and to move quickly, it's all about decision-making and making that as efficient as possible. I think another thing that was really important for Auburn's growth, and also for my growth, and also for bringing all these teams together, all these different people, was a really clear mission and purpose. And you can see them here on the right-hand side. It's referred to as our guiding star. And I think it really does serve this purpose. And it was really nice that Ira also shared the mission of DeepMind as well, and shared that she was inspired by that, because for me, it plays the same role. I'm very much inspired, and I think the team are as well, and that we align around this purpose and the mission of Auburn. And I can share that now. So our purpose is to shed light on the world's toughest challenges. And our mission is to unleash AI-powered imaging for everything and everyone. And that started with sexing, the sexing application, but we now also continuing this mission. Now we're bringing AI-powered imaging for everything and everyone. And here you see some examples of eggs, ED0 eggs, also nuts, fruit, and plants. And when you think about the potential impact that could be had here, it's really enormous when you think about the amount of spoilage, for example, in the food industry, and how we can really have an impact with something like early fault detection at various stages within these processes. In order to continue with this, we also need some more MRI scientists. So I'm also pleased to share that we are hiring for various positions for a senior MRI integration engineer and an MRI scientist. And that already brings me to the end of my talk. So thank you very much for your attention. I've been Jason Skinner. You can contact me by email just there, and you can find more about the job ads if you're interested on our website, and also the MRI Together job board as well. And I will be in Gathertown afterwards as well.